Hello, this video is a review of what happened in Tuesday's class. So if you were present, you might want to crank it up to double speed and rewatch it. But if you weren't here, watch it at regular speed. Just real quickly, we had looked in MATLAB at what happens if we don't have any damping. All right, there's a spring, just a mass on a spring just oscillating, and we see it would just go on forever. But we know in the real world, springs die down in their oscillations. So we're going to add some damping now. Okay, and this damping force will be resisting the motion, and so we can see the oscillations die down. Okay, now the level of damping we have now is called underdamping because it still oscillates. But it is dying off slowly in terms of the oscillation. So we have a decaying oscillation. As I increase the B value in line 19 of the code, the oscillations are dying faster and faster. So let me switch that up to a number like 1 and see what happens. Still oscillating, but we can see it's dying off faster. There's more resistance to the motion. If I make that a 2, let's see, it might not oscillate. It'll still oscillate, but dying even faster. Let me make that a 4 and see what happens. Now you can see it no longer oscillates at all. It's sort of decaying down towards equilibrium position, but it never passes it. So that's what's called overdamping, when we lose all of the oscillations. And so we have those various cases. Underdamping and overdamping, and then the border between those is called critical damping. Now you can see in the code, we've changed the force. Let me get down here. It has the Kx that we had before, but now we're subtracting minus a BV. So let me switch over to the theory behind this. Okay, so let me stop this screen share and switch over to my iPad. Okay, so when we have damped oscillations, we are saying we're going to add a damping force. Okay, and the damping force is negative BV. Okay, so just a couple quick things about this. Okay, first of all, it depends on the velocity. The faster you go, the more resistance there will be to the motion. Okay, it's like walking through water in a swimming pool. The faster you try to walk through it, the more you'll feel the water pushing back. The negative is because it resists. If you're trying to move to the right, it will push left. If you're trying to move left, it'll push right, and so on, up and down. If the mass on the spring is going up, the damping force will push down, and vice versa. And then B is just the damping constant. So when we put all of the forces together, we now have 2. We remember the old thing, we had F of E is negative Kx. So if we look at the total force, we get that F is now negative BV minus Kx, right? And then we can easily just substitute MA using Newton's second law for F. And we have MA is negative BV minus Kx. All right, and then if we bring it all over to one side, just to make things tidier, the math will be easier if we look at it this way. Okay, so we now have an equation with acceleration, velocity, and position in it, but we want to make this into a differential equation. So we know acceleration is the second derivative of position with respect to time. Velocity is the first derivative of position with respect to time, and x is just the position. So this is the differential equation for damped harmonic motion. Okay, now the solution for this equation is that x should equal e to the RT. Okay, We can see this is going to work nicely because we need a function whose derivatives are almost the same as the function. Okay, and quick little review: the derivative with respect to x of e to the x is just e to the x, but if you did the derivative with respect to x of e to the 2x, we know that's 2 e to the 2x by the chain rule. All right. The derivative with respect to x, if it were e to the negative 2x, that would be exponential decay. That would be negative 2 e to the negative 2x. In general, the derivative with respect to x is going to be of e to any number. Let's call this kx, would be k e to the kx. Now, in our derivation, we're switching over to r instead of k, and we're using t as our variable. So we can take the derivatives with respect to time, and this will be r e to the rt. And by the chain rule again, this will be r squared e to the rt. Okay. Now, if that's our solution, we should substitute it into the equation and find when it will make it true. Okay, so if we substitute into the equation, we'll get m times r squared e to the rt plus b times r e to the rt plus k e to the rt equals 0. All right, and we have a lot of things that are similar here. We have e to the rt in every single term, so we can factor it out. And so then we can bring that out to the front, e to the rt, and when we factor it out of the first term, we're left with mr squared plus br plus k equals 0, right? Now, you should know the zero product rule. When we have two factors set equal to 0, one of them must be 0 or both. But e to the negative rt is never 0. Okay, so the solution is that mr squared plus br plus k must be 0. That must be true in order to make the differential equation work. Okay, so this will give us a value for r that will make this whole thing work. Now, this is in the form that you've hopefully seen before of ax squared plus bx plus c equals 0. That's called a quadratic equation. All right, and we know the solution to that is x equals negative b plus or minus square root b squared minus 4ac all over 2a. In fact, you may have sung that before. X equals negative b plus or minus square root b squared minus 4ac all over 2a. So we just translate that into r's. So r equals negative b plus or minus square root b squared minus 4mk all over 2m. All right, so now we see there are actually two different solutions because of this plus minus here. One of the solutions for r would be where you add that, and the other solution for r is where you subtract that. Okay, so there are two different solutions for r. Okay, so r1 would be negative b plus the square root of b squared minus 4mk all over 2m, and r2 is negative b minus the square root of b squared minus 4mk all over 2m. Now, in the theory of second order differential equations, that just means there's a second derivative. There are always two solutions. All right. So remember what we guessed. We guessed up here that x was e to the rt. We've shown that can be a solution if r is either equal to r1 or if r is equal to r2. All right. So the full solution is the combination of both of those. So the full solution is that x is equal to any multiple of e to the r1t plus any other multiple, c2, of e to the r2t, right? So this is the full solution to the differential equation, okay? Now, how will C1 and C2 be determined? Well, that depends on starting condition, okay? So C1 and C2 depend on initial conditions. So we've seen that if we start at amplitude with no velocity, one thing might happen. This was when we had no damping. If we started at equilibrium with a velocity, something else might happen. And if we had a combination, a third set of things might happen. Similar here, the starting conditions will determine what C1 and C2 are. So we'll need at least two starting conditions in order to determine those. And in one of the later videos today, we'll look at how to figure out what C1 and C2 are from starting conditions. Now, what's going to be interesting and we'll address in the next video is the idea that b squared minus 4mk could be greater than 0. B squared, that's the part that's under the square root, minus 4mk could equal 0. Or b squared minus 4mk could be less than 0. Okay. Now, if we have this case, okay, we had seen in the video, this was, well, these answers will be real. You'll get two real answers, right? In the second case, you'll actually get rational answers for R, but it turns out we have like one answer with double multiplicity, okay? This is the break-even point, okay, between b squared, the damping, in other words, being bigger than 4mk, and b squared being less than 4mk. Okay, if you look at this, since b squared minus 4mk is inside of the square root, you'll end up with imaginary parts of your answer, and the answer will become complex. It'll have real and imaginary parts. Okay, so that's actually the more interesting case. Now, from the early part of the video, it turns out this corresponds to overdamping, and this corresponds to underdamping. Okay, so we actually, in our boxed-in equation, we have a good solution for overdamping. What we need to explore now is what happens when R1 and R2 are complex numbers, and we'll do that in the next video.